We want to look at this question related to total log probability and Bayes rule, where we're told that the diagnostic test has a probability 0.95 of giving a positive value when applied to a person suffering from a certain disease, and a probability 0.1 of giving a false positive when applied to a non-sufferer. It's estimated that 0.5% of the population are sufferers. Suppose the test is administered to a person about whom we have no relevant information relating to the disease apart from that he or she comes from the population. And you want to find a couple of probabilities. So the first probability that you want to find is that the test result will be positive. First, let's define the main events given to us in this question, the two main events. The two main events that we're interested in, one, the test gives a positive result, and the second, the person is suffering from the disease. So these are the two main events. We can define plus to be the event that the test gives a positive result, right? That's the first event. And the event S is going to be the person is suffering from the disease. So these are the two main events that we have defined. And now let's first figure out, so first let's define the main events given to us in the question. And now let's define the probabilities that are given to us already in the question before we find the required probability. So what we're given in the question is, so we're told a diagnostic test has a probability 0.95 of giving a positive result when applied to persons suffering from a certain disease. This is essentially the probability of positive given sufferer is 0.95. So it's this probability given to us over here. Right, so this probability is 0.95. This is given to us over here. The probability of positive given that he's a sufferer. And then we're told the probability that it's positive given that he's not a sufferer, IS complement, it's given to us as 0.10 over here. And a probability 0.10 of giving a false positive when applied to a non-sufferer, right? So the probability that it's positive given that he's a non-sufferer is 0.10 given to us, right? And we're told another probability as well. We're told the probability of sufferer, we're told over here is 0.5%, which is essentially 0.005, right? This is also given to us in the question. So this is information that is already provided in this particular question. So this is 0.005 and this is over here, right? Now, so we define the events and then we define the probabilities as already given to us in the question, right? So now what we'll do is we will use complement rule. Use complement rule to find any probabilities you can from given probabilities. From given probabilities in a Bayes rule problem, in a Bayes theorem problem. So what we're saying is, whenever you have a Bayes theorem problem, you first obviously define your events, and then you look at what probabilities are given to you. And then what you're going to do is, you're going to use the complement rule to find any probabilities you can from a Bayes theorem problem. So we know the probability of positive given he's a sufferer is 0.95. So the probability of negative given a sufferer is basically going to be 1 minus 0.95 is 0.05, right? We can write this as negative or as positive's complement, right? Either way is fine. The probability that he's positive, given he's not a sufferer, from this we can find the probability of negative, which is a complement of positive, given that he's not a sufferer, as 1 minus 0.1 is 0.9. And probability of sufferer is 0.05. So probability that he's not a sufferer, 1 minus 0.005 is 0.995. And here we need to note something. Note that probability of A given B plus probability of A complement given B is equal to 1, right? Because the probability of A plus A complement is 1, and this would be true in a reduced sample space also given B, right? So the probability, the test can either be positive or negative, and the probability of positive plus probability of the test being negative is 1. The probability of being positive and the probability of being negative given S is also 1, right? So this, even in a reduced sample space, the probability of all outcomes has to be 1, right? So that's why probability of negative given S is 1 minus probability of positive given S. Similarly, probability of negative given not S is the 1 minus the probability of positive given not S, because the sum of probabilities of all outcomes is 1 even in a reduced sample space. But This is not true in general. Probability of A given B plus probability of A given B complement is not equal to 1, right? So the complement rule here says if I know the probability of positive given sufferer is 0.95, then from here the probability of not positive given sufferer is 1 minus 0.95, because the sum of the probability of all outcomes has to be 1, even if you're looking at a reduced sample space. Even given S, you can either have a positive result or a non-positive result. So this is all the information that we needed that is given to us, right? Now let's do part A with this information. Let's do part A. Now in part A, what we're required to find is the test result will be positive. So required is probability, the test result is positive. Now notice over here, we want to find an unconditional probability, right? In this part, we want to find the unconditional probability the test result is positive. We're not finding a conditional probability. We want to find an unconditional probability, the probability the test result is positive, by conditioning on mutually exclusive and collectively exhaustive events, right? So we want to find this unconditional probability by conditioning on mutually exclusive and collectively exhaustive events. S and S complement, right? Mutually exclusive means they cannot occur at the same time. You can either be a sufferer or you can not be a sufferer. And the collectively exhaustive, which means that the union is the sample space. The sample space between two sufferers and non-sufferers. Right, so we'll use total or probability in this case, right? Because total or probability is, we use total or probability when you want to find an unconditional probability. In this case, the probability the test result is positive by conditioning on mutually exclusive and collectively exhaustive events. In this case, those events are that he's a sufferer and he's not a sufferer. So use total law of probability. What is the total law of probability? Let's just quickly recall. It's probability of A is probability of A given B into probability of B plus probability of A given B complement into probability of B complement, where B and B complement have to be mutually exclusive and collectively exhaustive. So using now, so in this problem, we have to use total probability. So using total law of probability, we can write the probability that he is positive is the probability he is positive given he is a sufferer into probability he's a sufferer plus probability positive given he's not a sufferer into probability he's not a sufferer. We have all this information. Probability positive given sufferer is 0.95, probability of sufferer is 0.005, plus probability of positive given not sufferer is 0.1. Probability of not sufferer we found using complement rule is 0.995. So this turns out to be 0.10425. So the first part was just finding the probability the test result will be positive. We want to find an unconditional probability by conditioning on two mutually exclusive and collectively exhaustive events given to us that he's a sufferer and he's not a sufferer. So in this case, we use the total of probability. Now let's look at part B. Asked us to find right. In part B, we're asked to find the probability that given a positive result, the person is a sufferer. So this is a here we're required to find a conditional probability where the observation is that we're given a positive result, right? So here we want to find a conditional probability. The first was an unconditional probability. So we're required to find the probability that given a positive result, the person is a sufferer given positive result. So we have one form of conditional probability. So here the idea is I have one form of conditional probability, have one form of conditional, so we have one form of conditional probability given to us here, which is the probability plus given as this probability, right? And we want to find its exact opposite, right? Probability as given as, and we want to find its exact opposite. So use Bayes rule, right? So we're going to use Bayes rule. Want to find its exact opposite, probability as given plus. So use Bayes rule. And what is Bayes rule? Let's just quickly recall. Probability A given B is probability B given A into probability of A divided by probability of B. Right, so remember, if you want to find an unconditional probability by conditioning on mutually exclusive and collectively exhaustive events like we did in part B, use total law probability. Bayes will be used when we're given one form of conditional probability, like in this case, probability of positive given sufferer, and you want to find its exact opposite. Exact opposite in this case is probability S given plus, right? So we want to find its exact opposite, so we'll use Bayes rule here. So now, So now if we apply Bayes' rule to this, probability S given positive, this is going to be probability positive given S into probability of S divided by probability of positive. Right? And in Bayes' rule problem, the denominator comes from the total of probability mostly, right? So the denominator comes, so in Bayes' theorem, the denominator comes from total of probability, right? Already found in part A, right? So this is where the denominator is going to come in this Bayes' theorem, already found in part A, right? So now we have all the information that we need. We have probability of positive given S is 0.95. We have probability of software 0.005. And probability of positive we found in part A at 0.10425 from a total of probability 0.04556. So in this way, we can solve this problem, right? In the first part, we use total or probability because we are finding an unconditional probability by conditioning on mutually exclusive and collectively exhaustive events. In part B, we use Bayes' theorem because you are given one form of conditional probability, probability of positive given S, and you wanted to find its exact opposite, probability of S given plus. So we can apply the Bayes' theorem.